Hello everyone, my name is Zijie. The authors of the paper cannot attend due to the visa issues, so I will do the presentation for them based on their notes. Then I will introduce this work. Stereo is a continuous modeling approach to stereo matching. So stereo matching is an important task in computer vision for depth perception. Given a pair of rectified images, the goal is, for each pixel in the left image, find the corresponding pixel in the right image, and then compute the difference of the horizontal coordinates, which is called disparity. The green circles in figure A and B illustrate a pair of matched pixels. However, since we have only a finite set of pixels, how could we compute the continuous scene disparity values? Numerous recent studies have undertaken the challenge of predicting continuous scene disparities, classified into two main categories. Regression-based approaches predict a real-valued offset by neural networks for each hypothesis of discrete disparity. The offset is then added to the discrete disparity hypothesis at the final continuous prediction. Typical examples include raptor stereo, CDN, and more recently, IGEV and DLNR. Classification-based approaches first estimate the categorical distribution for the discrete disparity hypothesis, and then take the expectation value of the distribution at the final disparity, which can be any arbitrary real value, even though the categorical distribution is discrete. Conventional stereo matching algorithms typically calculate a cost function that can equate to a probability mass function with a finite set of disparities. Yet, in real-world applications, the ground truth disparity is continuous. Thus, we propose to interpolate the discrete distribution by Laplacian kernel and compute the probability density function of disparity. To choose a value as the final prediction, we propose to minimize the following risk. Here, FYPM is called the risk at y, and LYX is the error function between y and x. By risk, we mean that if we take y as predicted disparity, how much error there shall be with respect to the ground truth. Since the exact ground truth is unavailable at the time for making the prediction, we average the error across all possible ground truth disparities with the distribution PXPM. Previous methods usually compute the expectation value of x as the final prediction for the disparity. We want to point out that we can arrive at the same prediction by using squared L2 norm laws. Nevertheless, it is well known that the L2 norm is not robust to outliers, and therefore we resort to L1 norm. Here, in figure A, the pixel in the right cycle is located at the boundary of the chair. Thus, the disparity distribution has multiple modes. Figures B and C show the discrete distribution of disparity hypotheses in orange bars. In figure B, the prediction obtained by averaging is blurred and far from any of the modes. In C, we obtained the optimal solution under L1 norm, which is more robust and closer to the ground truth. The green curves show the interpolated probability density. We propose an approach that enables end-to-end learning of the network. Firstly, the target function FYPM is convex with respect to y, so we compute the optimal solution where the derivative is zero by binary search. Secondly, to enable end-to-end training, we have to compute dy over dpm to propagate the gradient backward. We obtain the gradient by the use of implicit function theorem. The overall pipeline is shown in the figure. We first extract the multi-scale features from left and right images respectively. The subsequent procedures are divided into two stages. In the cost stage, shown in the orange arrow, we sample disparity hypotheses uniformly and match on quarter resolution features, while in the refined stage, shown in the green arrow, we match the half-resolution features efficiently. Disparity hypotheses are sampled centering around the disparity predicted from the cost stage. In both stages, we first construct cost volumes by concatenation and then apply the stacked networks to aggregate the matching costs. And finally search for the disparity that minimizes the proposed R1 risk. We evaluate our framework on the KITTI benchmark. At the time of writing this paper, our approach, labeled as risk mean, achieved top matching accuracy in the non-occluded image regions among the published methods. We perform ablation studies on the Middlebury to compare the expectation and the L1 norm risk minimization for disparity, prediction at training and test time. Even with expectation minimization at training time, we slightly improve the matching accuracy with L1 norm risk minimization at the test time. Yet, if we use the L1 norm risk minimization both at training and test time, the best accuracy is achieved under all metrics. More experiments can be found in the paper. Okay, so the paper concludes that continuous end-to-end trainable model for stereo matching is possible within L1 risk minimization formulation. It is shown that the proposed approach is beneficial to multi-modal disparity distributions and outliers and generalizes better on cross-domain stereo images. Stereo risk is unique in a way that it provides a new way of solving stereo matching with well-thought-out theoretical and improved results, enabling adaptations from fields such as robotics and control engineering. That's all. Thank you. And if you have questions, please contact the authors, but not me.